With that, we got the base of our movement done. But if we take a look at Genshin Impact, we quickly notice that this isn't how movement works there. Not only does the player rotate towards the movement direction, that movement direction is relative to the camera and not to the input. If we press W to move forwards, we'll always move forwards towards where we are looking at. That also means that if we press S, we'll move backwards or to the opposite of where we are looking at. To be able to do the same, we need to create a camera system. Thankfully for us, we are going to be using Cinemachine, which easily allows us to add one. This seems to be what Genshin Impact uses as well. We have already downloaded it when setting up the project, so we can now easily create our camera by right-clicking in the hierarchy window and going to Cinemachine Virtual Camera. I'll name it Player Camera. While I was able to somewhat replicate Genshin Camera with a free-look camera, there was a missing option that we will need to add ourselves, and apparently, virtual cameras are more performant as they only use one rig, while free-look cameras use 3. To start off with our camera, we need a target for the follow and look at fields. Follow is the target that our camera will follow around. Look at is a target that our aim will be relative to. By relative here, I mean that the center of our aim will always be on the target. To add this, select our player game object and add a new child game object named Camera Look Point. I'll add an icon to this game object so that we can easily see where it is placed. Then I'll make its y-axis be at 1.4. When that's done, we'll set our camera targets to be this new object. So back into our player camera, drag this new game object to the follow and look at fields. Note that Cinemachine should add a Cinemachine brain to your main camera automatically, but if it didn't, make sure you do it yourself. This simply makes it so Cinemachine cameras can control your main camera. Our camera is now looking towards our camera look point, but is still using the old input system, so our current mouse input won't work. Thankfully, it's quite simple to swap it with a new input system, as all that we need to do is to add a new component named Cinemachine Input Provider. This component accepts an X-Y axis, which will represent the camera rotation, and a Z axis, which will represent the distance. Of course, to assign an input here we need to create it first. So go ahead and open up the Input Actions window. In here, let's first create a new action for our mouse movement by pressing on the plus icon and naming it Look. For our types, we'll have it to be a value of vector 2 as we want to constantly get our X and Y axes. In its binding, select Mouse Delta. Delta is apparently the change in pixels in vector 2 since the last rendered frame mouse position. For our zoom, we'll add another action named Zoom and set it to value as well. We simply want a float here to know whether we are scrolling up or down. The value type for float is called axis. Now we'll use the value this input returns to know how much we should scroll up or down, but it currently comes with high values such as 120, so we'll clamp it to a lower value. To do that, add a processor of type clamp and set it to be from -0.1 to 0.1. This input also comes inverted, which means scrolling up will return positive and scrolling down will return negative. We want the opposite of that, so add yet another processor, but this time of type invert. When that's done, set its binding to be mouse scroll Y. Then save the asset. Back in our player camera, in the Input Provider component, select the corresponding inputs. So look for the X-Y axis and then zoom for the Z axis. We are now using the new input system for our camera. We are only a few settings away of having our camera behaving like Genshin's camera. The first thing we'll be doing is set our FOV to 60. The next thing is setting both the camera body and aim. The body sets the algorithm that the camera uses to follow its target. The aim sets the algorithm that the camera uses to look at its target. If we take a look at Genshin Impact camera, we can see that we can rotate around the target. In the free look camera, this is known as an orbital transposer. However, in the virtual camera, the orbital transposer does not contain a vertical rotation, but only horizontal. Thankfully, we can imitate the free look camera setting using the framing transposer body together with the POV aim. The framing transposer tries to keep the camera center to the follow object at the provided distance. The POV aim moves the camera according to your input, which should translate to where you are looking at relative to the look at target. If we enter play mode, our camera should have the same orbital behavior that Genshin Impact camera offers. However, there are a few problems. Besides the camera movement being too fast, the faster you move your mouse around, the slower the movement gets. What we want here is for the camera sensitivity to be as close to the mouse speed as possible. To fix that problem, open up the aim area and swap both inputs from max speed to input value gain. Make sure your vertical axis also has the inverted option enabled, as otherwise we'll be rotating towards the opposite vertical direction. Next, we'll set the speed on the vertical axis to be 0.1 and on the horizontal axis to be 0.16, as Genshin camera has a faster horizontal movement. If we now move our camera around, it should be slower and also have a closer one-to-one sensitivity with our mouse. If you wanted a fully one-to-one sensitivity, then you will need to set the speed to 1. There still are some problems left to resolve. One example is our vertical axis, as we aren't able to rotate 90 degrees up or down. That's solvable by updating the value range field from the vertical axis. We'll set it to be from -90 to 90. For our horizontal axis, we'll go with 0 to 360. I'm not entirely sure if we actually need this one, but I'll leave it as is to make sure nothing breaks. I'll also enable wrap to allow the camera to keep rotating once we get to the 360 degree rotation, as otherwise it will stop there and we will need to move the camera back. The next thing is that if you start moving your camera around and stop it, you might notice something. The acceleration and deceleration of the camera are instantaneous. In Genshin Impact, however, there is a small acceleration and deceleration. We can easily set that up by updating the vertical and horizontal axis, axle time, and decel time fields. For the vertical axis, we'll go with 0.8 acceleration and 0.05 deceleration time. For the horizontal axis, we'll also go with 0.8 acceleration but 0.25 deceleration time. Our camera shall now start or stop a bit slower. I'm not really sure what the recenter target does here, but I have mine set to follow target forward, and it works fine, so I'll add it here as well. In this case, it seems to be the same as the look one because both have the same target, but I don't really know what these axis angles are relative to target means. I'm assuming it has something to do with the vertical and horizontal recentering, and that it recenters relative to that target, but I'm not completely sure. If you don't know, please leave a comment below explaining it so that we know what it actually does. This horizontal recentering option is what Freelook cameras don't provide us with, but we'll only need this quite a bit later, so leave it disabled for now. For our body, we'll be setting both the X damping to be 0.2 and the Y damping to be around 0.4. Damping is how fast or slow the camera tries to keep itself centered with a target, which in this case should be the follow target. While we won't be needing to set this here, I'll also go ahead and set the camera distance to 6. We now have a camera working quite nicely, but we still need 2 more things to take care of. The first one is that currently our camera goes through the ground instead of colliding with it. The second one is that we can't yet zoom in or zoom out. Thankfully, both are quite easy to do. Let's start by exiting play mode. For the camera collisions, go to the bottom of the Scene Machine component and open up the Add Extension dropdown. There should be an option named Scene Machine Collider. Feel free to press on it. This should add a new component to our camera object that allows us to set collisions with the camera. What we want here is to set the Collide Against layer to something to collide with. To do that, we'll create a layer for our environment so that the camera collides with every existing environment instead of just the ground. So add in a new layer named Environment. Then go to all of our environment cam objects besides the water and set their layer as environment. When that's done, go back to the camera and now set the Collide Against to environment and remove the default layer from there. For the Ignore tag, we'll set it to player. Of course, we need to add this tag to the player, so select its game object and add the player tag. Next, back into our camera, we'll be changing the strategy of the camera collider. This is simply how the camera behaves when colliding with something. In our case, we want the camera to pull forward when we collide with the environment, which simply pulls the camera to the front of the collider. I'll leave the rest with its default values, but feel free to change them if you want to. If we enter play mode, our camera collisions should be working. That means that all that's left is our camera zoom. Unfortunately, I don't think there is a built-in functionality for this, so we'll have to do it ourselves. Thankfully, with the input provider, set axis and body camera distance, this is quite simple to achieve. That's because the input provider set axis gives us a value of when we scroll our mouse wheel, while the camera distance is how far we are from the target. So go back to the scripts folder and create a new folder named camera. Inside, we'll create a new C# script to which I'll name camera zoom. When you are done creating it, add it as a component of our player camera. Then open it up and remove the default methods. We'll start by creating 3 variables: the default distance that the camera will start at, and the minimum and maximum distance that the camera can go to. So type in serialize field, private, float, default distance, and default it to 6f. Then duplicate the variable line twice and swap default with minimum, and then default with maximum. I'll set their default values to 1f and 6f respectively. We'll also make it so we can update these variables with a slider. So to do that, simply add in after the serialize field attribute range from 0f to 10f, meaning we can choose a value from 0 to 10 through a slider. Next, we'll add 2 more variables: a value to smooth our distance lerp and a value to multiply our set axis value with. So duplicate one of the variables above twice and then change the first one to be named smoothing and the second one to be zoom sensitivity. I'll default the smoothing to 4F and the zoom sensitivity to 1F. That's all the data we need to be able to set in the inspector. So now we need two more things. A reference to the Scene Machine framing transposer, which represents our body, and a reference to the Scene Machine input provider, which contains our set access value. So create a new private variable of type Scene Machine framing transposer named framing transposer. Make sure you import the Scene Machine namespace. Then create another private variable of type Scene Machine input provider named input provider. To get their references, we'll use the getComponent method, so type in awake, and inside type in framing transposer equals to getComponent of type Scene Machine virtual camera, which gets our virtual camera. We'll now get our framing transposer by using the .getSceneMachineComponent method instead. For the type, we'll of course pass in Scene Machine framing transposer. We use the getSceneMachineComponent method here because the body is part of the Scene Machine component. For our provider, type in input provider equals to getComponent of type Scene Machine input provider. When that's done, call in the MonoBehaviorUpdate method and call in a new method named zoom. We can now start zooming our camera. The way we'll do that is by retrieving the value of our scroll, which we can do from the input provider set access. To do that, type in float zoom value equals to input provider dot get access value. Here we need to pass in an access index, which is the index of 2 for the set access. Then we multiply this value by our zoom sensitivity. We now need to add this value to our current distance target, which we currently have no variable of. So above, create a new private float named current target distance. This will start with a default value of 0, but we want it to start with a default distance. So in the awake method, type in current target distance equals to default distance. Then back in our zoom method, type in current target distance equals to current target distance plus zoom value. We need to make sure we clamp this target distance to not pass our maximum distance, so add in matf.clamp surrounding our assignment, and then pass in minimum distance as a second parameter and maximum distance as a third one. We can now lerp the current distance towards the target distance so that we slowly get there instead of it being an instant change. To do that, create a float named current distance and assign to it framingtransposer.mCameraDistance. Then type in if current distance equals current target distance, we return. This makes it so that if we are already at the target distance, we won't do anything. To lerp our value, type in float lerped zoom value equals to mathf.lerp current distance, current target distance, smoothing multiplied by time.delta time. We pass in smoothing multiplied by time.delta time here because we don't really want it to be an amount of seconds for the whole lerp, but just keep it as consistent as possible at every change and get there whenever it gets there. Then finish it up by setting the framingtransposer.mCameraDistance to be equal to the lerped zoom value. That's all we need to zoom our camera, so save it up and go back to Unity. If we now enter play mode, we should be able to zoom our camera.